As it turns out, there are different classifications of acids, and we're going to look at here a really broad classification, which is strong acid versus a weak acid. And let's recall that when we have an acid like HCl in water, it dissociates and it gives up that proton. H plus is literally a proton. Hydrogen is a proton and an electron. It's got a mass of 1, generally speaking, so there's not even a neutron. We make it positive. That means we remove the electron, and what we're left with is H plus. So when we have HCl, it makes acid because it's making H+. When we have a base, like sodium hydroxide, NaOH, we learn that NaOH, like NaCl, dissociates completely. It creates Na+, which we don't worry about, and OH-, that's our unit of basicity. And remember here that when we say an acid or a base, we are talking about H+ and OH-, but we don't just have like a bottle of H+ or a bottle of OH-. We bring them as part of larger chemicals, in this case HCl or NaOH, that pretty much supply just what we're looking for, right? And HCl and NaOH are sort of the most classic textbook and laboratory examples of getting just the acid. Chloride Cl- is pretty inert. It's not going to react with anything. So HCl gives you H+, and something that doesn't really do anything else. Pretty much just H+. NaOH gives you Na+, pretty much doesn't react with anything, inert, and OH-, therefore sodium hydroxide gives you hydroxide. But it's important when you see sodium hydroxide or hydrochloric acid HCl that you say, well, this is the reaction that occurs, and what's important is the H+ or the OH-. Now, when it comes to acids, we have strong versus weak acids, and it's really important to know that when we have a strong acid, the definition is that it dissociates completely. This is to say HCl goes to H+ and Cl-. If we have 1 mole of HCl, it becomes 1 mole of H+. If we had 5 molecules of HCl, it would become 5 molecules of H+. This is what defines it as a strong acid. It separates completely into H+ and Cl-. And it's not a huge list of strong acids. Here's the list here. You don't need to memorize this. I really think knowing HCl as your strong acid is the most important. But know that strong acids dissociate completely. And this idea that things in chemistry either go to completion or not to completion is what we looked at with equilibrium previously, right? This is a non-equilibrium, non-reversible case. We call them strong acids in acidity. So 1 mole of HCl would make 1 whole mole of H+. Nice and simple for the chemistry of strong acids. In contrast, weak acids like acetic acid, CH3COOH, the acid in vinegar, which we'll see this notation. This is a condensed structural formula. We'll explore this more in organic chemistry. It describes the structure of acetic acid a little bit better than if we group all of the C's and O's together. But anyway, acetic acid dissociates less than 100%. And if we are to write out this example, well, we do have the H+ dissociating, but it's an equilibrium reaction where it's incomplete dissociation. It sets up at some percentage less than 100%. If we have 1 mole of acetic acid, CH3COOH, we get less than 1 mole of H+, because it's a weak acid. It doesn't dissociate completely. And really, really importantly to our understanding of weak acids, the conjugate of acetic acid, which is the leftovers, the acetate ion, right? It becomes CH3COO-. We call this the conjugate base of acetic acid. And we call it that because it is a base, right? This reaction can go forward and backward. This is to say that the acetate ion can accept a proton. That's the definition of a base. Acetic acid can donate a proton by giving it up. Acetate can accept a proton going in reverse as this reaction is written, and therefore can act as a base. And that's a really important principle for when we look at buffers and how to stabilize pH in our next video.